welcome everybody to this webinar on steam network optimization with proven examples from the process industry. That is a very important add-on to the title, in fact. Today we have a large audience, and that proves that utilities and steams are a hot topic today. When I asked about 2 years ago to an operation manager in Europe, what do you pay for a ton of steam? The answer was always and quite consistent, well, about 20 euros. And that was even very consistent in a large area of the world. Now, when I ask that question today, the answer is still consistent, but it always starts with the same sentence, it's terrible. And then the number that they mention is very often a number with 3 digits. So we talk about 100, 110, 120 euros for a ton of steam. So multiplied by 5 or 6. So time to have a look on how steam can be produced and consumed in a most optimal way with smarter control and optimization. And that's exactly the topic of today. Now, if you have any questions, please use the chat box to type your questions. We will answer them at the end of the session. You do not have to wait to raise your questions. You can already start doing it right now. So by just typing your questions in the chat box. Today's webinar will be recorded as usual, and you will all receive a link very soon. Perhaps today, latest tomorrow, you will have the link. And I sometimes get a question via email later on if it is allowed to share the links with others. And the answer is, of course, the more the better. So please do not hesitate to share the link with your colleagues or even some other people from other industries that you know, no problem at all. We also have today 2 poll questions to start the webinar, and perhaps we should start with the first one. And that's the following here. How do you control your steam grid today? So as today, So with a simple set of base layer controllers, meaning a couple of PID loops, with advanced process control, with advanced regulatory control. So you have base layer controls, but you do smart things with them. With APC, advanced process control, or do you even add APC and then on top of it an RTO, think like Aspen Utilities or Visual Mesa or GDOT or these kind of things. So that's a little bit the question that I have. So how do you optimize or control your today's steam network? And while people are voting, I clearly see that the majority of the people, they have a very simple base layer control system. Some of them, about 35%, they have some more intelligent base layer controllers. But what you see is that only 5% have APC on their steam grids, and 2% have something even above APC, which is RTO. Good. Okay. And then the second question, which is also the last one, and the question is, do you think that you lose a lot of energy due to the lack of optimal control? So the fact that due to the fact that you have no optimal control, that's an important sentence, because not if you have very suboptimal boilers, that's not the question is because you have not optimal control, do you lose a lot of energy? And there it is very clear that many people vote yes. There is definitely room for improvement on the control and optimization side. And about 20% of the people say, I even have no idea. So I don't really know if I can improve my controls or my steam network by doing better control. And then things like studies and so on might be of use. Okay, many thanks. So let's move on. I will start with a very short introduction to IPCOS before I give the floor to Juan Carlos. Voilà. Do you still see the poll?
Is it the full screen now?
No, okay. Good. So IPCOS is a service company founded in 1995 with 7 offices around the world, and we are active with about 80 engineers on all continents out of these 7 offices. Yeah? And the credo of IPCOS, which you can see on our homepage, is we deliver digital solutions ready to meet the world's toughest industrial challenges, increasing plant productivity, reducing emissions, and adapting to demand. So, and that's exactly what we do. Yeah. Now, next slide, please. Digitalization, yeah, that can mean a lot of things. And this slide shows you what we offer in this large digitalization space. Yeah, I highlighted some items which are very relevant for this today's webinar, but in fact, all of the items what you see over there are important when you talk about utilities, steam, energy, and so on. Yeah, but today we're going to focus really on better control and optimization of steam networks by doing smart PID control, yeah, by doing advanced process control, and also by making models, simulations of steam grids, yeah, and of course things like emission monitoring and lowering emissions. That is of course the end result or one of the main results of optimizing steam grids. Lower fuel consumption, lower emissions, yeah, that is key these days. Good. So we are ready to start, and I will come back to you after the presentations, but let me first introduce Juan Carlos Duarte, the presenter of today. Yeah, JC, we call him. Yeah, JC has more than 13 years of experience in process control and optimization, has been within IPCOS for about 10 years now, yeah, and he's executing projects in oil refining, gas, petrochemicals, fertilizers, and utilities. So he does studies on utilities. He executes base layer optimization projects, simulation projects, and advanced process control projects in all these industries, but also linked to utilities. So that means that Juan Carlos is one of our best people that we can have here to present today's webinar. So, okay, JC, the floor is yours. And for all the attendees, if you have any questions, please fill them in on the chat box, and we will. I will come back to you after Juan Carlos' presentation. Voilà, JC, please go ahead.
Thank you very much, Christian. Yes. Yeah, fortunately, I have experience in all of the things I'm going to talk about, first-hand experience. So I wanted to divide the presentation into 3 chapters, let's say. The first one, dynamic simulation, basically like going from the basics to the more advanced to see what is the approach that we give to steam networks, to energy production in general within IPCOS, to make, to really go deep into the problem and try to find the best solutions. So not only we work on the automation part of it, but we also work from the beginning doing dynamic simulation of steam networks, for example. We have done that in the past. So I have a simple example here. Well, not simple, it's just an example here, something we did some years ago. This was a company who is actually a utilities company that provides with high pressure steam to a chemical complex. And then they had several boilers and they wanted to remove an existing boiler and install a new one. And you would say, well, that doesn't seem like much of a problem. But the problem was that the distance between the boilers was massive. The existing boiler, as you can see in the picture, was 1.5 kilometers from the two normal, from the current boilers, this one here. But the one they wanted to install was almost 6 kilometers away from those initial ones. So you can imagine that a lot can happen in 6 kilometers of pipe. So if you want to use all of the boilers to have control of the network, you do need to have an idea of how the dynamics work. There will be some delays, there will be some responses that are not the same. So in this particular case, what they had as an issue as well was the fact that because There were consumers in between. Sometimes the steam flow had to be reversed. So sometimes the flow of steam went all the way from north to south. Sometimes it went from south to north. And that requires special control strategies. So what best way to do that than to simulate it? And so we did that. We use a dynamic simulator with all the thermodynamics, of course, simulating the pipes. And then we simulated the boilers. The simulation of the boilers, this is a bit of an extract of that simulation. I think probably most of you know which simulator we were using. Here is how we simulated the boilers. It was a simple simulation in the sense of we just simulated as heat exchangers, both the convecting and the radiant section, but we did simulate very precisely the volumes, especially the volume of the steam drum, because that changes the dynamics of the boiler itself. And all the control strategies around that. So you can see that we were simulating the level of the steam drum as a 3-element control. A level controller for the steam drum, but we were also simulating things like the desuperheater with the feed-forward action that is included, all the let's say advanced regulatory control strategies were also implemented in the simulation, and based on that, that will give you a more accurate representation of what it was all about, and then we were able to do the job. Things like turbines, we also went and established, the performance curves. We input the performance curves of the turbines that were used at site, just to be, again, as accurate as possible in the simulation. I told you, it was very long distance between the boilers, so we use steam pipes. So we simulated the pipes as accurately as possible, because we had to account for heat losses, we had to account for load losses. All that had to be looked into to avoid situations like a potential condensation on the pipe and so on and so forth. So apart from the fact that we understood the dynamics of the process very well, and that allowed to improve the PAD controls in terms of the strategies that were there already, and the tuning that had to be done, we also managed to design new controls. So these new controls, like for example, this anti-backflow system. As I said, sometimes the flow of steam goes from north to south, sometimes from south to north, but you cannot just switch between the two without a special operation. So that special operation requires a lot of care. But in normal operation, if the demand changes, then you need something that protects you from the flow suddenly reversing, because that sudden flow reversal would cause a lot of problems in the pipe if you don't do it with following a certain procedure. So yeah, the simulation allowed us to design very specifically, very accurately the way this anti-backflow system had to be implemented, included all the calculations and all the controls that had to be implemented. So yeah, here you see as the simulated example of how this anti-backflow system would work. And yeah, well, I'm not gonna enter into details, but basically it's just avoiding the flow to go to zero. In fact, the minimum flow was going to be, in that case, 30 tons an hour, whatever was the case. So yeah, there was some special controls that was making sure that that was the case. Basically, one of the boilers was typically under pressure control, so pressure control was acting on the boiler, but once this reverse flow was detected, then it was changed to a different kind of control. So what we concluded is that even for very fast process dynamics with lots of disturbances, dynamic simulation can actually be configured and used to troubleshoot process control problems, and we definitely saw that, because we included all the steam suppliers, all the consumers, and we played with that. So we managed to simulate all the disturbances and see how the network was going to respond to that. And then the impact of big changes in those processing units, like in this case, changing the boiler, or remove one and install another one, it can be anticipated, and then you can, act on that. The downtime of the units can be reduced if robust controls are in place. That's one example. Then there's another example that is currently going on, and it's another network we're also doing a dynamic simulation of. But in their case, they actually want the simulation to try and improve the control. They are not going to change boilers, but yes, they want to evaluate some changes in the consumers and see how those additional disturbances are going to impact the network, and how can we improve the controls for the network. So this can bring a lot of value. It seems like it's just simulation, but it can bring a lot of value because it gives you a very good starting point. Instead of just using, standard controls, if you do this beforehand, you start off with a much better place. Then after that, when everything is implemented, then we also do the base layer optimization. Basically, we go and we review all the control strategies that have been implemented in the place. So they can greatly improve your operation. And we also do, of course, the PID tuning of all those loops. Sometimes those loops are interactive. I mean, they interact between each other. And we have the experience and the knowledge and the tools needed to be able to do proper PID tuning, in which we avoid those interactions from becoming, continuous oscillations or unstable behavior in the plant or in the network in this case. So this example was a utilities plant in France. We were asked to improve it was a bit of a complicated one, a cold fluidized bed steam boiler. It was not your typical gas boiler, natural gas boiler, or I don't know, any other kind of easier fuel. This was a cold fluidized one. So we had to re-enable the unused, but in that case, existing base layer control. So many things had to be done. Basically, you can see here how there's a whole management of the coal itself, the fluidized bed, and how the steam pressure controller is actually acting on many parameters. So what were the issues we found? That the steam pressure controller, which is basically the most important one in any single network, was in manual. So the network was unstable. The pressure was never stable. It was just operators making manual actions on the boiler. The fluidized bed temperature, which you can imagine in a boiler like that, is really important. Was also in manual, so it led to poor combustion conditions. The steam flow was also in manual. The primary air was in manual. There was also poor settings for the excess oxygen, so low efficiency. The desuperheated temperature, that was also not working well. So what we did was just basically make sure that the base control strategies were working fine, performed well, and then improve some of them with advanced control strategies. So here we have the example of this is the pressure control. You can see how before it was just manual actions, and after that it became an automatic control, and then it was staying at the value that it was set to stay at. And same thing happened with most of the rest of the controllers. We managed to improve the way they were working. Basically from manual to auto. You should see a difference. But here in this case, just going that step forward and going to automatic was really challenging. Then you can see things like, the temperature controls, that this one was also a lot more stable because we had an automatic control there. And this was the excess oxygen, for example. The excess oxygen Before that, yeah, it was not that great. But after better control was achieved, then they were able to reduce the amount of excess oxygen, which all of you must know that typically lead to energy savings. The superheater, for example, this is another one. This is a very clear example of what can be done. Here it was more about a better use of the feed-forward action. So a bit more of like an advanced strategy to use here. So the load to the boiler was used as a feed-forward to help control the superheater much better than it was done before. And yeah, it was greatly appreciated. So conclusion, several loops were tuned and taken successfully in auto mode. The steam pressure and the flow fluctuation were significantly reduced, and improvements, of course, associated to reducing the excess oxygen from an average of 6% to 2.5% were achieved. Again, this is energy savings. And then lastly, I'm just going very quickly over the things. We can talk about details whenever you need me. I mean, just pop the questions there, and then we will talk about them later. Just to go quickly through all the slides, then that's why I'm just not very specific in details at the moment. And then the last example is the MPC, multivariable control optimization, and APC basically. So sometimes the base layer control is not enough when optimizing utilities systems. And when I say not enough, is that usually is in cases in which if you would want to do the control that kind of control with an advanced regulatory control, it would become just too complex to operate. And then multivariable control actually makes it easier to implement and introduces some flexibility in the control. So yeah, it can help uncover the potential that otherwise with just base layer control probably wouldn't have been able to do. And then the reduction in emissions and energy consumption are typically the most common benefits from an advanced process control implementation. So this example is a utilities plant and a steam network in Italy. So we were asked to improve the steam network and power generation performance by reducing the energy waste and stabilizing the pressure of the three networks, the high pressure, medium pressure, and low pressure networks, the steam networks, of course. This is a small example. I mean, we show how it works. Basically, what we have here is a cogeneration turbine and boiler, basically. Yeah. So this is a gas turbine. This gas turbine is generating electricity, obviously, but then the exhaust gas is used as heat, partially as heat for one of the boilers, and then the rest of it is just provided with natural gas. At the same time, you have some turbines to generate even more electricity using the high pressure steam. So you can see how the high pressure steam is used here by these two turbines to generate even more electricity. So what happens here is that these generators, they are consumers of high pressure steam, and there could be, like, let's say, a kind of a competition between the boiler and the generator for the control of the high pressure steam. So that competition was difficult to handle in just basic DCS controls. So that's why we had to use APC or MPC, and that really helped dealing with that interaction and reducing the energy consumption. So as is the case for most of the steam networks, the steam production and demand is in a constant unbalance because, sometimes they just don't match, which means that there's a continuous venting of steam, and sometimes without the need to. Sometimes it was just because the boiler was not fast enough to respond, or because the power generation was not set at the value that had to be set to avoid the venting. So with this, what I'm trying to say is that sometimes you were trying to generate so much energy, so much electricity, that at the end you ended up venting up some steam, like over-consuming the high-pressure steam. And that was not the case. I mean, the idea of those turbines was to utilize as much as possible the steam, but not so much that you ended up having to vent some of it. It is extremely fast process dynamic kind of process, which is an interesting thing to mention because this is still an advanced process control, but it was running at a much faster frequency. And yes, and then of course we have the common use of direct letdowns, which in this case also go against the power generation. If you let down steam through a valve, okay, you gain in a bit of steam production, but you lose in power generation. And depending on your prices, you might be interested in one or the other, but typically power generation wins over generating a little bit more of steam through desuperheatings in letdowns. So the solution was basically a dynamic control of both the high pressure network and low pressure steam network. So basically the pressure of the network was controlled by the APC itself. Again, that meant that the controller had to run at a fast frequency. In this case was 10 seconds. For all of you that are familiar with APC, you know that typically APC controllers run every minute, sometimes every 2 minutes, depends. But this was running every 10 seconds just to be able to act fast enough, and it was acting fast enough. Another advantage of using APC is it's very easy to use that feed-forward action of just measuring the steam demand and acting based on that. And as we said, we were handling directly the power generation, so then the power generation was also in balance with the amount of steam that was produced. So here we have an example of what we achieved. So before APC was implemented, the average natural gas consumption of the boiler was roughly around 1,200 kilograms an hour of natural gas, and then it was reduced to all the way down to 900, 850. So this was great in terms of energy savings or gas savings. Total calculated payoff of this project was over 2 million euro back then, when gas prices were not that high as they are right now. And then we also managed to stabilize the low pressure network. You can see how before APC was implemented, the low pressure network was changing basically almost 0.5 bar up and down. There was just no control, which the implication that it has on the rest of the plant, on the rest of the refinery. This was an oil refinery, so you can imagine that a lot of units were using low pressure steam as heating medium for reboilers or whatever kind of equipment that we're using the low pressure steam for. So when you have a much more stable low pressure steam pressure, then that is greatly appreciated because that brings also stability to the rest of the units. And then not only that, but we also managed to reduce the amount of letdown. So all that steam that was not directly let down through valves was then let down through the power generators. So that meant an increase in power generation. So the conclusion is that, again, even for very fast process dynamics with lots of disturbances, then advanced process control is actually a good candidate and can provide proper control and optimization. Okay.
Good. Yeah, this one.
Yeah.
Take the previous one, please.
I think I'm right on time.
Can you take the previous slide?
Oh, yes, just a second. This one?
Yes. Okay, just leave that on for the moment. Good. Okay. Thanks, Juan Carlos, for the presentation. I have, in the meantime, a couple of questions in the chat box, but please, if you have more questions, raise them all in the chat box, and I will go from one question to the other. So while you are still typing a couple of questions, let me start with the first ones. Good. This is about boiler models. What kind of, so if you do all these simulations and so on, what kind of boiler models do you use? Is that simplified, or is that high fidelity models? Is combustion a part of the model scope, or is that just very simplified? So can you elaborate on that, please?
Yes, because what we were looking for is the dynamic behavior. Then we were not so much interested in the combustion part of the boiler. So let's say, yeah, the internal geometry of the boiler was not that relevant apart from the volumes themselves, which are the ones that have the most impact on the dynamics. So as I mentioned before, it was basically the radiating and convection sections that were simulated as heat exchangers, of course, with the correct volume for them and the correct pressure drop across them, but still just heat exchangers. So yeah, we didn't focus so much on that combustion part, on the geometry of the boiler inside, and more on the dynamics themselves. So it's you could say it's a simplified model, but it's simple that is easy to simulate, but not so simple that it doesn't allow you to replicate the controls around it. So as I showed, we were able to replicate all the typical controls that you have around boilers.
Okay. Well, I have a couple of questions around these models, extra questions, so perhaps we can combine them a little bit. And that's about, let me just read it for you. What can you do to overcome speed change limitations inherent from the boiler feed itself? Yeah. So slow-moving, great-burning coal or recycled material, very slow to adapt the speed. How to limit steam release to the atmosphere in case of client fast load reducing. So I think is combustion is well, first of all, combustion is very simplified, but there are also delays and very slow dynamics possibly in there. So first of all, you have to simulate them, of course, and then the question is then how can you overcome the fact that, well, boilers tend to be slow on the feeding side, and how do you deal with that on a modeling and a control?
I don't know what do you mean by slow. I suppose depending on the fuel that you use, then yeah, like if you use like a coal boiler, then I suppose those are slower.
So speed limitations inherent from the boiler feed itself. Slow moving, great burning coal. So if everything goes very slow inside,
it's okay. Yeah, in those cases, if we're talking about something like coal, yes, in those cases, we will have to worry a lot more about the combustion itself. And then one thing that I didn't mention was that when we do this dynamic simulation, we just don't do it like that. We actually parameterize the simulation based on real-time data. So we use real-time data to try to make the simulation match as much as possible the real thing. So there's many things that we could do. There's we can put some rate of change limiters for the way the heat increases or decreases in the boiler. So yeah, simulation gives you enough flexibility to actually account for those kind of things.
Okay. Because that's also one of the questions, how to obtain your models for simulation. Do you use a prior knowledge theory, or do you also use data-driven modeling for updating the models, for example?
It's a combination. It's like, well, first of all, let's start with the fact that it is a simulator. So everything, all the calculations inside are based on thermodynamics, basically. Well, thermodynamics and fluid dynamics and all those things. And then the way we do it is we start off by replicating the whole topology of the network. We replicate it in the simulation, and once we have it, then we start using real data to compare the values of the simulation to real data, and then we adjust the simulation. So, for example, there's things like the load loss, the pressure loss on the pipe. That is something that, even though one of the things we ask is things like data sheets for the pipes, still it probably is not exact. So we better use real data, and then we change things like the roughness of the pipe. So in the simulation, you can change the roughness of the pipe and then use that parameter to make the simulation match the real pressure drop across the network. Same thing with heat loss. So we use temperature measurements across the network to also estimate the heat loss of the pipes with the environment, and then make it match. Yes, so it is a combination of things. But in the core, it's still simulation based on engineering first principles.
Because there is a question where wait, how to run MPC? There is somebody says I'm interested to understand how MPC is simulated in the dynamic simulator, but I think that's not the scope that you do, huh? So you build a simulator.
I mean, it could be done, especially in that simulator that we use, that most of you know which one that is. I'm just not going to mention it, but to avoid any advertising. But in that simulator that you use, you can, if you want, not only simulate the base layer controls, the PID controls, but you can, if you want, simulate an APC of that same company, of course.
So that means that you hook up the simulator to the APC and then run it in closed loop.
You can, yes, you can hook it up. Yes, there's a way for you to hook up the simulation to an APC, yes.
Okay, good, huh? And because you mentioned that you are going to also simulate the base layer controllers, but I assume that you also then simulate all the logic, because there are a lot of interlocks and all these kind of things that you also do that, I suppose, huh?
All of that is done, yes. All of that is done, as I was mentioning before. Yeah, all of that is done of high-low selectors or split ranges or you name it, yes.
Okay, good.
All those things are simulated. Yeah, cascades, feed-forward action, those things, or all of them are simulated, yeah.
Yeah. One very specific question. I don't know it. I think it refers to one of the examples that you give. How did you use turbine power as MV?
Yes. Well, it was fairly easy. You just send the set point to. Well, actually, it was just like that. The turbine power was a parameter you could just set on the DCS itself. They had the system already through the turbine governor, with which you could just change the power, and then automatically it did all the changes in the turbine for it to produce that power.
Yeah. It's just a steam consumer where you say you have to consume as much steam.
Yes, and then of course it has a measurement of the energy produced, but that's probably not that difficult. So it is kind of like a PID loop that controls the amount of energy produced by the turbine. So it was easy enough. It was just sending the set point, to be honest. Yeah.
Another question is, how did you calculate steam demand for considering it as feed forward?
You use steam demand?
Yeah, so how do you calculate the steam demand to consider that feed forward? So I suppose one of your
Yes.
end customers is consuming steam, and you use that as feed forward to optimize your complete grid or some boilers or.
Yes, that's what you do. That's what you do. Typically,
Question is, how do you
depends on what
calculate
you're
the steam
doing.
demand?
Sorry, what do you say?
The question is, how do you calculate the steam demand? So that's how
Well,
I read it. How do you
how do
calculate
you
it?
calculate it? Well, it's basically you make the sum of all the consumers. You probably have, I mean, to be able to do that, you need to have a flow measurement of the steam going to the different consumers. Otherwise, it will be, yeah, just a wild guess.
Yeah.
So
I suppose that person, well, it's just that question. And I have nothing more, but perhaps they want to also to know, assume you can predict or what the steam consumption will be for the next 5 to 10 minutes or so, because a plant is shutting down or so. Can that be used as feed forward, or do you use that as feed forward, or you just use the
the thing is,
actual measurement?
yeah, you need the actual measurement for sure.
Okay,
Yes.
so you don't the actual and then the forecast that you don't do. You just use what you do, consume now.
Yes. Yes. Yes.
Okay. How do you run the APC algorithm on a Windows machine or Linux? Yeah. Well,
Windows machines is
that comes
always
from the
Windows.
fact that it runs very fast. Yeah, but 10 seconds is still not hard real time. So.
Yeah, exactly. The thing is, before, yeah, in the old days, it was difficult to run the APC in normal Windows machines. That's why in the very old days, APC used to run in the DCS because DCS was the faster machine you could find. But nowadays, a simple server allows you to run many APC applications, and you can run them at a very fast frequency, 10 seconds, 5 seconds. It's not a problem. Especially because those applications are not huge. They are not like, I don't know, 50 manipulated variables with 100 control variables. No, it's not like that. It's a lot smaller than that. So yeah, without problems, a server nowadays is able to run an application at a very fast frequency.
Okay, good. There is a very dedicated question about high pressure steam and mid pressure steam and so on. For that gentleman who asked this, we're going to contact you directly for that because it's on the bits and the bytes. So, but no worries, we will contact you to explain that to you. Yeah. Can you please indicate how you typically approach a steam control and optimization project? What is the duration of a typical project from generating a simulation to an integrated control and optimization solution?
Okay. We have done the separate bits. We have not done the whole way from simulation all the way to APC for a single company. So that's what I'm saying. We have done it, but not for a single company. What we have done for sure is from the base layer control all the way to APC. Yes, we have done. Now from simulation, no. But if we just analyze it by pieces, then a dynamic simulation project, well, it depends on how complex the network is, and how many special cases do you want to run and want to evaluate. But I would say a simulation project could last something like 3 months or so, between building the simulation and then running different cases and, proposing new strategies. And then from there on I would say, is the typical duration of an advanced process control project, which would be another 5 months roughly, especially if we have to do a lot of changes in the base layer controls. The thing is, talking about timing, it depends on so many things. This time I'm giving is like averages, but in some places it could be faster. Depends on how much time does the client have available to do it, because it's not only our work, it's actually a lot of combined work between the client and us. Like for example, if we need to do changes in the base layer strategy, changes in the DCS, is it easy in your company to do those changes, or do you need to do like a big management of change that needs signatures from every single manager? So every single change you do, it takes long time. That can take months, even if it's just to make 2 new PID controllers. In some other places, the control team has the power and they can just do changes just the very same day if they are convinced. So yeah, it's a difficult thing to answer, but just giving averages, I would say that. Start to finish, I would say 8 months to 10 months, that would be, if you do the whole thing from simulation all the way to APC.
But perhaps it's also important to mention here that most of the questions we got for regarding a simulation project were more with the intention to evaluate future changes in the sense of we want to add boilers, build an extra one, change our control philosophies and so on. So for risk mitigation that they say, can you do a bunch of analyses for us? More on the base layer side. So it is not mandatory that you start first building a simulator before you go for APC. Huh? So we did all of these things, but the main reason for most of the simulation project was most of the time more on what if analysis. Can you design a new control philosophy for a whole steam grid based on the simulation, so that this is not a trial and error exercise because the whole site depends on it. Huh? So that's more often the reason why people ask for simulations. Good. Yeah, is IPCOS limited to a single MPC simulator platform? Well, I already can answer that. The answer is no. We are technology independent, which means that we can install and maintain any common MPC technology which is on the market. Yeah, and the same holds for simulators. Yeah, so that's not a problem. And again, we come back to that fast thing. Huh? So how do you guarantee real-time requirements on Windows machines? So yeah, well, real-time, we are not in the microsecond business. Yeah, we are still in the 10-second business, and a server that only has to do one thing, which is APC, yeah, has plenty of time to work in 10-second cycles. Yeah.
Yes.
Of course, you don't have to put Pi servers and or IP21s and RTOs and a dashboarding and a web server on top of it. But if that server has nothing else to do or not, plenty of time.
And I can tell you this. Actually, I can tell you this bit. In 2 of the cases where we have APC running 10-second frequency, that is not the only application running on that server. So we have the example of one place in which that application is running alongside another 3 applications. All of the other ones running every minute, but still another 3 applications running. And in the other place, we have that application running with another 5 applications.
Yeah. So, but all these things are scheduled, and sometimes you have applications that when they are getting a request, they start using a lot of computation power. And then, of course, that's unpredictable. But if everything is sequenced and time sliced, then it should be no problem.
I have only one example in which we had a limitation, and the limitation was not the server. It was a case in which we did again an APC for a steam network. We wanted it to run as fast as possible, but the fastest we could make it to run was 20 seconds. But the reason was not the server. The reason was the fact that the communication was difficult. The communication was going to be through OPC, but because of IT demands and whatever, they had to put an OPC tunneler in between the DCS and the APC, and it was the tunneler, the one that was delaying the signals from coming faster to the server. So that was the reason why we had a limitation. It was not the server itself. It was actually the communication.
Remember that one. Mm-hmm. Okay. Do you have examples where energy prices, for example, are used to determine the control optimum? So where the price of the electricity or the steam or whatever is part of the optimization equation, let's say.
It's not directly part, but Typically, yes, what we do is we use those prices to establish the optimization direction of the controller. And then if required, those things can be changed. But is it something like the client has to update every month or so? Not necessarily, no.
Well, I
But
think
can it be done? Yes, it can be done. It's not difficult to do, but we have not done it so far because, again, I think in the past it was a more flat rate of prices, so I think they were not worried about that. But I suppose in the new projects that we will be doing, that will become commonplace.
And prices changing on
With
an hour
changing
basis.
prices, yes.
No.
Then you can do that for sure, yes.
Okay, what's your experience on how to control several boilers in parallel? One slow, one fast, or two at the same pace that might disturb each other? So two
Great.
boilers in
Well,
parallel.
we can go back to the first example, the simulation example. Yes, we have experience with that. You can control them in parallel. I mean, you can use them in parallel. Depend on how slow is the slow one, of course. But you can do things like using filters to basically homogenize the dynamics, if that's what you need. I mean, if you have one boiler that is too slow, well, chances are you probably are better off using that boiler at a fixed production, steam production, and then using the other ones to control the pressure. That can be done. But if you have a boiler that is a bit slower than the other ones, you can still deal with that just by using filters. Basically, the signal that is coming from the master controller needs to go through some filters to basically accommodate itself to the dynamics of the other boilers. So yeah, it's something we have dealt with.
Okay. What other equipment will be needed for the optimization project? So does the customer need to buy something extra to make this happen besides a server?
No, I mean, sometimes not even that. If it's just an optimization of the regulatory control, there's nothing that you need to buy, provided that your instrumentation is in good shape, obviously. Mm-hmm. Because as is the case for any type of control, the instruments are the eyes of the control. So if the instruments work okay, the control will most likely work okay. If the instruments fail, then there is no chance for control.
But you don't need to buy anything extra to have an APC on a steam grid if the instruments, the regular instruments are okay.
Just the server for the APC, yeah. But,
indeed, yeah. Okay, good. And then ARC, so Advanced Regulatory Control, you can also put that on a steam grid. Now that you can make it as complicated as you want with a lot of feed forwards going from one to another and so on. And would you then combine that with APC, or do you at a certain moment say, stop, don't make it more complicated and lift everything to the APC, or you combine these two, or what's the best strategy here?
Oh, I think we are actually facing one of those cases right now, and when we tried to envision an advanced regulatory control, it was getting so complicated that actually even the client said, "Stop there. Let's just do the basics in the regulatory control, and for the more complex strategies, let's go for APC because." Yeah, it's just easier in that case. I mean, you can do a lot of things in the DCS, but they can get so complicated and difficult to maintain that sometimes you need to go for APC instead. It's easier.
Good. We still have time for a couple of questions. Have you developed a health indicator for boilers before it was used in an MPC solution, for instance, preferential loading?
Oh, okay.
You understand the question? I don't.
Yes. In fact, yeah, the project in France that we did, yeah, it was more indicator. It was basically when we defined the strategy of the APC, we did see that there was a boiler that we wanted to send more load to when controlling the network. That was done through biases. Basically, you had you had a master pressure controller acting on the boilers, and then through a bias block, you sent more load to one of the boilers or not. And that was based on efficiency. So we had an online measure of the online calculation of the efficiency of the boiler. And based on that, we decided to send more load to the more efficient boiler. Yeah.
Okay, good. Yeah. Coming back to that slow and fast boilers, the gentleman asked an extra question. The thing is that if you have two identical boilers or similar boilers, yeah, and in order to work optimally with them, is it then better that you treat one as slower or you steer it slower than the other, or that's
No. Actually, well, from my experience, if you have two boilers and they're almost the same, use them both because it's double the power. It's
with the
twice the power,
same
basically.
speed? Don't treat one slower than make one slower than the other. Like this is the
No,
master
I
and the
wouldn't do
other
that.
one.
There's no point because again, if you have two boilers and then just use them both because it's twice the power, twice the ability to respond to disturbances. I mean, just think about it this way. If you have a disturbance of 10 tons of steam and you need to react with the two boilers, well, if you react with them at the same time, then each boiler only needs to provide 5 tons. Whereas if you have one that is slower than the other one, then one will have to provide, I don't know, 7 tons and the other 3 tons. So, the one that has to provide 7 tons has to do more work, let's say. Whereas if you keep them even, then you have basically more controlling power.
I think that's well, we have a lot of questions which are sometimes very similar to each other, so I sort of make the average question out of similar questions.
Okay.
Can we tune a controller to behave differently at different range of output, like 5 to 10%, and then one from 10 to 100%? It's a strange split that was made, but I think the question is clear. Huh?
I have a feeling it's talking about split range controllers.
No, I think it's really like the process behaves differently in different ranges of operation mode, and that you tune your controller differently from a range from low to mid and from mid to high, for instance. I think that's how I read the question.
Yes. And in fact, it's something that needs to be done sometimes when handling different boilers. Like if you have a single pressure controller handling 3 different boilers, then the gain of the PAD control, the proportional gain, that one has to change depending on the amount of boilers that you're using. Same thing, because you have more or less controlling power, let's call it like that. So yes, you can do that through calculations, you can do that, and you probably should do that to keep the same performance. Because if you have initially 3 boilers, but then you go from 3 to 2 boilers, then those 2 boilers have to do more work than if they were just, if the 3 of them were working. So it means that your control has to send a stronger signal, if you get my point, to have the same performance. So yes, that can be done. That's one example. Or sometimes you just have processes that are so non-linear that if you study them enough, then you can probably develop some kind of gain scheduling technique in which, depending on the measurement, you change the controller proportional gain. Usually the integral time often remains the same. Depends. You can also check that, but at least the proportional gain can be changed based on process conditions. That can be done. We have done that in many situations because it's very nonlinear processes. That's called gain scheduling, and yes, it can be done.
And that typically is valid for base layer controls, huh? Because but the question is that also applicable to APC, where you need different tuning for different kind of loads, for instance?
Yeah, for sure. Yes, well, APC is even more flexible, so yeah, you can do many things. Yeah.
But do you need it? Do you need to tune your controller, APC controllers, depending on the load, or can you just deal with one tuning? That's how I read the extra question I got.
Yes. It all goes down to the process behavior. I mean, yes, if the process response is different enough, then yes, most likely you need to have some kind of and for APC it's called transformation, some kind of transformation or something that makes the control behavior to be different depending on the region of operation that you're at. So yes, can you do it? Yes, there's many ways of doing it.
Okay.
There's standard functionality like transformations in APC, or there's calculations that you can make. Same thing, you can also apply some kind of a gain scheduling strategy for APC if that's what you require.
Okay. I think that's about it regarding the questions. Again, we didn't answer every individual question because a lot of them were similar. So I took a little bit the average of all the questions I received. So I want to thank everybody for attending this webinar. Yeah. And as I said at the start of the webinar, we have recorded it. We are recording it as we speak, and we will make it available to everybody, and you will receive the link in the next couple of hours or max days. Yeah. So I thank you again for participating in the webinar. If you have very particular problems or questions that you say, well, can we discuss this for my application or for my plant or for my steam grid, then please contact me. You see my email address over there, my phone number over there. Please don't hesitate to contact me, and then we will get back to you. Yeah. Voila. So Juan Carlos, many thanks for the presentation, for the webinar, and to all the participants. Again, also thank you very much, and I hope to see you again at the next webinar. It will be announced very soon, so you will get an email. And if you know some people who also want to attend these webinars or at least get invitations, then also drop me an email with their email addresses and their coordinates, and I will be happy to add them to our emailing list so that from now on they will also be invited. Yeah. So okay. So for now, have a nice evening, have a nice day, have a nice morning or night, depending on where you are in the world, and I hope to see and hear from you very soon. Okay.